So Josh, do you want to introduce our speaker?
Sure. So it's nice to be back at UT. Thank you guys for inviting me back for Girmohanta's talk. He's I guess a friend of mine that I've never met in person, but we share a close friend in Robert Schrock from Stony Brook, who is his PhD advisor, as I understand it. And so Sudha's been doing some interesting work over the last couple of years, written some influential papers on beyond standard model physics, primarily those of baryon-number-violating modes, including neutron-antineutron transformation, which of course is a focus for UT through Yuri and formerly myself there, and lots of interesting stuff with I guess you could call them extra dimensional models and whatnot that can maybe even predict a future where we do observe this interesting process that can potentially govern the genesis or baryogenesis that we want to try to find the mechanism for. So without further ado, I'll turn it over to Sudha. And I guess, Sudha, do you mind us asking questions throughout, or prefer kind of
sure.
at the end?
Yeah, you can ask questions throughout. Yeah, just stop.
Great. So we'll turn it over to you.
Okay. Thanks, Josh, for the very nice introduction. And thank you, Professor Yuri Kamishkov-Torfa and the University of Tennessee for inviting me to present our work on new results on nbar oscillations and baryon-number-violating nucleon and dinucleon decays. So this is the overview of my talk. I will first motivate the baryon-number violation. Then I will provide the improved lower bounds on partial lifetimes for baryon-number violating nucleon and dinucleon decays. And I will then move on to discuss baryon-number violation in a model with large extra dimensions and present standard model effective field theoretic analysis. And then I will discuss nucleon decays and nbar oscillation in a left-right symmetric model with large extra dimension. I will briefly comment on neutrino masses and mixing in models with large extra dimension, and then I will conclude. So let us discuss the improved lower bounds on partial lifetimes for nucleon decay modes. First, we ask that what is baryon number? Well, this is the field content of the standard model as we know it. And we can ask the question that why is electron stable? And the answer is that it is stable as it is the lightest charged particle. And in the standard model, the charge is gauged as E1 and is unbroken. We can ask a similar question that why is proton stable? And we can give a global quantum number defined as 1/3 number of quarks minus number of anti-quarks, and observe that this is an accidental global symmetry of the standard model. So why do we expect baryon number violation? Well, it is an accidental global symmetry of the standard model, and it is violated in many ultraviolet extensions of standard model. For example, in grand unified theories, this violation is natural as quarks and leptons are placed in the same representation. In passing, we just note that in the standard model, baryon number is already violated by SU12 instantons, but the rate is negligibly small at temperatures low compared with the electroweak scale. On the other hand, baryon number violation is one of the necessary conditions for explaining the observed baryon asymmetry of the universe. Hence, a number of dedicated experiments have searched for the baryon number signature, violation signature, namely nucleon decays, and obtained null results, setting stringent upper limits for the rates for the nucleon decays. In passing, we can just show one such mode in a water Cherenkov detector like Super Kamiokande. So consider P goes to E plus pi naught. The emitted positron will be above the Cherenkov threshold, and the emitted pion would immediately decay into 2 photons. Thereby, the resulting signature would be 3 Cherenkov vortex coming off from a single vortex, corrected for the Fermi motion of the proton. And also in passing, we just note that a detector like Super Kamiokande can distinguish between an electron light and muon like event, as electron being a lighter particle would undergo several secondary collisions, producing a more fuzzier reading than muon. These are the current experimental bounds on the partial lifetimes for different nucleon decay modes. A factor of 10 to the power 33 here has been taken out. And these are the references for different experiments. As the outgoing neutrino is not detected in an experiment, it can be both electroweak singlet or non-singlet. We will generically denote them by this symbol nu. We'll first derive an approximate relation between the rates for different nucleon decay modes. And then we will combine this relation with the experimental bound for one mode, which will give us an estimated bound for the other mode. Our estimated bounds are more stringent than the existing direct experimental bounds. So as we have already seen, the established experimental bounds imply that the baryon number violating scale lies much above the electroweak symmetry breaking scale, and thereby the effective Lagrangian is invariant under the full standard model gauge group. These are the effective 4 fermion operators violating nucleon, mediating nucleon decays. Q is the quark doublet, L is the lepton doublet, alpha, beta, gamma are the color indices, IJ are weak indices, A is the generational indices, and C is the Dirac charge conjugation matrix. In effect, this produces this 4 fermion operator connecting 3 quarks with 1 lepton and thereby mediating nucleon decay. We will work in a minimal theoretical framework in the sense that we take standard model plus only beyond standard model physics that produces this local 4 fermion operators. Before deriving the approximate relation, let us remind ourselves that the decay rate of a parent particle with mass Mn to final states consisting of n particles with mass Mi is given by this formula, where S is the symmetry factor, Drn is the phase space, and A is the amplitude. It's useful to consider the phase space by itself. And for the case when the daughter particles are much lighter than the parent particle, we can also extract appropriate powers of the mass of the parent particle to define a dimensionless phase space Rn bar. This is the two-body phase space given by the well-known triangle function lambda. We will denote by a subscript naught to represent the cases where the daughter particles are much lighter than the parent particle. Okay, so let us consider the Feynman diagram for P goes to L plus M, where L is the light lepton, E or mu, and M is a pseudoscalar or vector meson. This can come from these 4 fermion operators. For example, U can go to L plus and D conjugate, and then D can come along and produce a bound state with this D conjugate to produce this M, or this M can come from a bound state of U and U conjugate. But note that this D can come along and annihilate with this D conjugate to produce a final state photon, or that can come from an initial or final state Bremsstrahlung radiation. We subsume all those possibilities in these diagrams. And this immediately suggests that we can relate the decay rates for these 2 different decay modes. Namely, there is a factor of E, the electromagnetic coupling in the amplitude, hence the factor of E square in the decay rate. And the phase space differences can be taken into account by introducing these factors of R for the appropriate final states. And inverting this relation for the decay rate would give us the appropriate relation for the partial lifetime. So thus we relate the decay rates for 2 different decay modes, and we can use the experimental bound on one of the decay modes to infer bounds on the other one.
I'm sorry, can you explain the lower diagram? So it seems that you introduce direct coupling of the baryon with lepton. Is it due to some baryo-leptons, or how you draw this diagram?
Right. So this, we have assumed that we have these 4 fermion operators as our minimal theoretical framework, as standard model plus beyond the standard model physics producing these 4 fermion operators. So this connects 3 quarks with 1 lepton. For example, you take this operator, this connects UDU with L, And you can conjugate this to produce the L in the final
Yes,
state.
I am asking about what is inside this blob. What is the mechanism? It is not point-like interaction, right?
Yeah, this is a point-like interaction. The
Point-like.
is an
This is
Yeah.
an effective field theory, so it's point-like.
Yeah, the unknown UV physics is much heavier than the scale we are interested in. So that has been integrated out, and the blob represents that integrated out physics and giving rise to these effective operators. Yeah, so this blob represents the heavier physics being integrated out, which violates baryon number.
So this is the phenomenology effectively.
So
It's not
Yeah,
that means there are some mechanism inside, something like rank unification, particles exchange, which is at a very high scale, and you effectively see it as a four particle interaction, point-like.
yeah, right. Yeah, we subsume the UV physics into this effective operators. That's right. Yeah. Okay. So we get this approximate relation for two different partial decay modes. Similarly, we can consider n goes to nu bar m and relate this with n goes to nu bar gamma. And as in the previous case, we obtain this relation. Similarly, this gamma can occur as an internal line and can go on to give us an L plus L minus pair, or this can also come off from an internal Z line. So this has a factor of E square in the amplitude, hence a factor of e to the power 4 in the decay rate, and a 1 over q square propagator factor is cancelled by similar kinematical factors coming off from the fermion spin sum. And this involves a non-trivial three-body phase space integration, which in turn demands the full knowledge of the UV physics as you are asking. So in the spirit of approximate relations, we only take into account three-body phase space suppression introducing this R3 bar, the dimensionless three-body phase space. Note that at the energy scales considered, the virtual gamma will dominate over the virtual Z in the amplitude by a factor of 10 to the power 3. So we have to only consider the virtual gamma contribution. Okay, so similarly, we can relate the partial lifetime of n goes to nu bar L plus L minus with n goes to nu bar m. And we obtain this kind of relation. For the case where these outgoing leptons are different, so L and L prime, this can come by an internal W line. So this gives up a factor of GF, the Fermi constant in the amplitude, which has a mass dimension -2. And the only available mass scale to cancel that mass dimension is the mass of the neutron. So we have a factor of GF Mn square in the amplitude. We take a square in the decay rate and invert that to obtain the relation for the partial lifetime. So we obtain a relation of the partial lifetimes, and here the phase space ratios of two-body and three-body phase space are appearing inside that. Similarly, we can consider modes like P goes to L plus nu bar. Again, the neutrinos are not detected in an experiment. This all has signature of P goes to L plus x bar, where x denotes weakly interacting particles or antiparticles which do not decay in the detector. Note that GF MP square is 10 to the power -5. So this yields a strong suppression of the decay rate. And using the bounds on the partial lifetime, this yields a much stringent bound on the partial lifetimes of this type of decay mode. Okay. So similarly, we can consider diagram for n goes to nu bar nu, which has the experimental signature. Is there a question?
And there's just a crazy storm here.
Okay, so which has an experimental signature of n goes to invisible. So this is mediated by an internal Z line, and we can again similarly get a factor of GFMN squared whole to the power -2. And this is just coming off from the phase space factors. We can Also using similar arguments, we can get the following bounds for continuum photon emission. These photons are to be differentiated from the cascade photons produced by the decay of pions or eta, because in an experiment, those can in principle be distinguished by momentum selection. So this is our result. We have extracted a factor of 10 to the power 33 here. These are the different decay modes. The second column represents the experimental lower bound on the partial lifetime. And the fourth column is our estimated lower bounds. And these bounds of IMB3 were much old. They were not updated. And after our paper got published, the Super Kamiokande improved the bounds on the modes of charged leptons. So this is the updated result, including the updated Super Kamiokande bounds on the 3 charged lepton final states. And as the relations are only approximate, we only note down the order of magnitude for the estimated lower bounds. So as we can see, the lower bounds are much stringent than the current experimental bounds. Okay. So we have derived improved lower bounds and partial.
Can you explain why they are more stringent?
Sorry, can you repeat the question?
Can you explain why they are more stringent?
Why they are more stringent?
Yeah, why theoretical are more stringent? Proton decay was not observed, so that is early to compare the branchings of for different modes.
Yeah.
But are you going to say that the current experimental limits are in agreement with theoretical estimates and allow the existence of this decay with a little bit more experimental effort? What's your message?
Yeah, our message is that given the minimal theoretical framework, namely a gut type 4 fermion operators along with standard model physics, the estimated lower bounds on the partial lifetimes are this. So the modes are in an experiment, it would be harder to search for these modes. But on the other hand, if these modes are observed in an experiment, then it would imply existence of lower scale new physics than which is not assumed in this minimal framework of gut type 4 fermion operators plus standard model physics. And the reason that these bounds are stringent than the current experimental bounds is that, for example, the bound on P goes to E plus pi naught is much stringent than the bound on, say, P goes to E plus gamma experimental bound. And what we have derived is we have derived an approximate relation between the 2 different decay modes. And then we use experimental bounds on one of the modes to infer bound on the other mode. And as the bound on, say, P goes to L plus M, where M is the meson, is much stronger, hence the inferred bound is also stronger. And there's a factor of, say, e to the power 4, as you have seen, or GF MN square, or GF MP square, whole to the power -2, which yields a factor of 10 to the power 10 for these modes with the internal Z or W line. Does that answer the question?
Are they basically all based off of the experimental bounds for the first 2 rows? Is that accurate?
Yes, we use experimental bounds on the P goes to L plus M to infer bounds on, say, the other modes.
You mentioned proton to pi 0 positron. It is not in this table.
Right, we use that experimental result to infer bounds on the other modes.
But it is the toughest bound.
Yeah.
Experimentally, which exists.
Yeah, exactly. Exactly. That's why we use it to infer bounds on the other modes.
But it is not in this table.
Yeah, it's not shown here because we don't estimate the theoretical lower bound on that mode.
Why can you explain in few words why your estimates are different from the previous calculations made by many people in the framework of SU5 and supersymmetric SU5 and in many different models. What is new, which is different in your calculation as compared to the previous calculation? You also mentioned at the beginning that you are providing better estimate than it was provided previously.
Yeah.
So maybe I can try to put it in maybe simpler terms, and Sudha, you can tell me if it's wrong.
Sure.
But effectively what they've done, Yuri, is they've taken a single experimental value, which is a recognized lower limit, and then they've created a general theory that integrates out high energy scale observables, where effectively they use the same framework, which is in some respect not dependent on any particular model, whether it be supersymmetric or SU5, et cetera, but they use that throughout, and then they scale everything according to that known experimental lower bound. And so what that does is in a very general way say that if you know this experimental lower bound, and if this broad theory fits into the context of any model, you can't do better than this.
But the calculation is done on effective field theory, so that you don't consider the detailed effects. Like, for example, in original SU5, you have put some particles with some masses, with some couplings. And by the way, Bob Schrock contribute to that. The matrix elements of that. And I don't see that how you, using effective theory, you can do more elaborate, more better predictions.
Right. So what the point, as Josh mentioned, is that all the new physics is actually inside this box. So for example, all the theories has to obey the experimental bounds for the prediction of P goes to L plus M. What we all are saying that given that those theories obey the bound on say P goes to L plus M, we just tack on standard model parts and use the experimental bounds on P goes to say L plus M and infer bounds on the other modes. So we are not predicting the bounds on the decay rate or the partial lifetime of P goes to L plus M in any specific model from effective field theory or whatsoever. We are not predicting that. We are not doing any better job than full UV complete model like SU5 or something. We're just saying that given the bound on one mode, say P goes to L plus M, and taking the minimal effective framework, we are not introducing any new physics. It's standard model. We are just tacking on standard model vertices and relating these two different processes and using one experimental lower bounds on the partial lifetime to relate the bounds on the other one. So all the physics, UV physics is inside this blob, which is the same in these two decay modes. So they are basically scaled out.
Well, I apologize that I'm distracting you. But
no. Those are important questions.
Model only, but there is no baryon number violation in the standard model.
But he's just saying the ratio of these processes.
So if your prediction are also concerned the tau over branching, and you are saying that in the standard model there is a lot of information which can be used for that, that can be considered.
I suggest
right. So we are only.
And we can come back. I mean, if you want to,
okay, maybe,
if you want to say a
I
quick
shouldn't
thing,
interrupt you.
yeah.
Sure.
I think there's another point that will come later, which is that these are not so favorable for proton decay, but that they're not necessarily disfavorable for other modes.
Okay.
And so that's part of the added point that'll come.
Yeah. So, okay. So we were here. And let us now move on to discuss improved upper limits on baryon number violating dinucleon decays to dielectrons. So neutron, anti-neutron oscillations are another kind of baryon number violation that has received considerable attention in the literature. This violates B by 2 units and also B minus L by 2 units. It was noted early on that this might provide the source for baryon number violation for baryogenesis. We note that nbar oscillations are mediated by 6 quark operators, and hence the effective Hamiltonian has coefficient with mass dimension -5. In contrast, the single nucleon decay operators has coefficient of mass dimension -2. So naively, one might expect that nbar oscillations will be highly suppressed when compared with single nucleon decay. But the assumption of a single mass scale responsible for baryon number violation might be oversimplified, and new scales may suppress nucleon decay while mediating nbar at a rate comparable to current experimental limits. So we will provide an explicit example of that later in this talk. The experimental signature of an nbar oscillation is that there is a finite transition probability for an initial n to transit into an nbar, and the transition amplitude is denoted as delta m, which is basically the off-diagonal element of the effective Hamiltonian in the nbar basis, which in turn says that the physical neutron is a mixture of n and nbar, and there is a finite probability of an n to annihilate with a nearby n on p, producing dinucleon decays, which is the experimental signature of this. So the searches for nbar oscillations has been in 2 frontiers. For the free neutron beam, in field-free vacuum, the effective Hamiltonian in the nbar basis looks like this, where delta m is the off-diagonal elements, representing that the n state can turn into an nbar with this probability. This has been searched for in ILL Grenoble, and they obtained a bound on delta m, which is this. Of course, they were not dealing with field-free vacuum. They had to deal with the Earth's magnetic field, so which splits this level and suppresses this mixing. So they had to arrange for the degaussing of the Earth's magnetic field and also the propagation time of the ultra-cold neutron, so that there was an intricate cancellation among the suppression effects, thereby enabling them to probe the physics of delta m. Also, there has been searches for nbar oscillations in bound neutrons in nucleus, and the effective Hamiltonian for this case looks like this, where the nbar experiences an imaginary potential, which reflects that there is an annihilation probability of this nbar inside this nuclear environment. So this says that the physical neutron state is a mixture of n and nbar, and the mixing angle is given as so. Of course, this mixing angle is highly suppressed, but this is more than compensated by the large number of nucleons present inside a detector like the Super Kamiokande. From these matter instability searches, Super Kamiokande inferred bound on delta m, which is this, and they updated the bound by a factor of 2 or so in recent years. These nuclear effects has been calculated by many people, including our own Josh Barrow. Specific final state searches have yielded bounds on the partial lifetimes for nn goes to a specific final state. We'll now show, as in the previous case, that using bounds on this, we can infer bounds on nn to dilepton final states. So
Well,
about minimal theoretical, yeah.
You can explain that you are talking about n bar. That means that the neutron transformed to anti-neutron, for example, inside the nuclei, and you are talking about 2 nucleon decay. That is another crossing channel of this reaction, right? Neutron decay into hadrons is another crossing channel of neutron anti-neutron annihilation, because it is not clear how they are connected.
Right. So what I'm saying is that, as you correctly pointed out, that a physical neutron is a mixture of n and nbar, and hence sitting inside a nuclear environment, it can annihilate with a nearby neutron or proton due to this nbar component. And this comes from this mixing and the effect of n-nbar transition. So the effect is, as you said, the dinucleon decays to multi-pion final states dominantly. Yeah, okay. So our minimal theoretical framework is again the standard model plus beyond standard model physics encoded in the effective Hamiltonian. So this is the diagram mediating Nn goes to L plus L minus. So N transit into an N bar, this blob again represents effective interaction. The UV physics has been integrated out. This proportional to delta M, an amplitude of transiting into an N bar, which can then annihilate with a nearby neutron to produce an internal gamma or Z line, which can then go off to give us an lepton pair. Note that this is the same vertex which can mediate Nn to 2 pi. So again, this contains all the UV information, and given the bound on Nn to 2 pi naught, we can track along the standard model part, and we can relate the modes for Nn to L plus L minus to Nn to 2 pi naught. Note that as the energy is considered, the photon dominates over the virtual Z. Only the total angular momentum not equals to 0 state contributes for the vector current. It is easy to show that the ground state for Nn is J equals to 0. So along with this factor of E square in the amplitude and hence e to the power 4 in the decay rate, we introduce additional factor of Tnn J not equals to 0 to denote the probability of Nn to be in a state J not equals to 0. So again, a specific UV model can predict a rate for Nn to 2 pi naught, say for example, but this has to obey a experimental bound, and we use that bound to infer a bound on Nn to L plus N minus. And this is our inferred bound. So even with this probability, which is less than 1, taken to be 1, the bound on Nn to L plus L minus is this one for E or mu. Similarly, Nn to nu bar processes can be considered, where this N bar annihilates with an N to produce a virtual Z line that then goes up to give nu bar. Again, this contribution mainly comes from J not equals to 0 state, because for J equals to 0 state, the vector part gives 0 contribution, and the axial vector part gives a contribution which is proportional to the mass of the neutrino, which is negligibly small. So again, this gives a factor of GF in the amplitude, and to cancel the negative mass 2 dimension, define S equals to twice Mn square available energy. This GFS square appears inside this relation.
So this diagram, that means that the Z and gamma you showed previously interact with the violation of baryon number 2.
So all the violation of baryon number is in this blob. This gamma and Z has nothing to do with the violation.
I look globally into N bar. You draw here 2 neutrons. I will treat it as initial state, and then these 2 neutrons are actually you produce the mechanism of how the Z and gamma will interact with the delta B equal 2. And I don't understand where
at the Z vertex, the baryon number is 0.
So this is N bar goes to L plus L minus. Yeah, as Josh pointed out, the only
what does it mean it's 0? I will take globally Nn 2 nucleon violate. I don't know what is in this vertex.
So if the blob doesn't exist, this process doesn't exist, because you cannot go from N to N bar. Only with this introduction of blob, we can go from N to N.
How about conservation of spin in this vertex?
It doesn't change the spin. This is effective Lagrangian is invariant under the spin. It doesn't change the spin.
No, a photon and Z has a spin 1, and the neutron has a spin 1/2, and this is S wave.
Right. So this 2 N and N bar can annihilate into a gamma and Z, right?
But you said this is neutron transformed to anti-neutron, so it is like a motion of the single neutron.
If you have spins that are aligned, you can do this.
If you would have 2 neutrons, you can do that. But if you transform neutron to anti-neutron, then it is like a single neutron is moving and interacting with gamma or Z.
So I agree that the magnetic moment flips. That's true. But if you have a spin half plus spin half, in general, if you have alignment of some kind, then you can, I believe you can do this at that vertex.
So
So if you have incoming spin half, and then you have outgoing nbar, which is if you have spin negative half.
here, the God is protesting.
I mean, there's just a finite probability for n to annihilate to an n bar, two spin halves combining into a spin line.
Mechanism is not consistent.
So I think that Yuri's broad question here is why do I care if the annihilation process occurs, if you will, on this line versus the Z vertex? And I think broadly, what does that do to the total amplitude?
Well, that was the reason why people, starting with Mahapatra and many others, draw a more complicated diagram. They introduced the Majorana baryons in the state, and you are trying to do it with gamma and Z. Yeah, if this is true, then in E plus and minus colliders, I should see what I should see, production of the two baryons with violation of baryon number. If I consider inverse channel.
Yeah, but the rate would be highly suppressed. Here, the flux of initial NN is much more to produce or probe this effective BNV, but to go from this direction to this direction.
But you are saying that it is contained. Okay, I probably should keep silence.
Yeah, okay.
Discussion for offline.
Right. So we were here and n into nu bar, and again we have a similar kind of relation for n into nu bar and n into 2 pi naught, and so similarly we can consider np2l plus nu l, and we have a similar relation of np2n plus nu l with np2 pi plus pi naught. So this is our final result. These are the different decay modes. The second column represents the experimental lower bound, and the fourth column is our estimated lower bound. And again, we use a bound on NN to multiply on to infer bounds on the dileptons. So they are stringent than the current experimental bounds, and observation of these decays with partial lifetimes much lower than estimated here would imply the existence of new physics that has been not encoded in the minimal standard model plus age effective framework. So right now the discussion has been model independent effective field theoretic analysis. We will now discuss the baryon number violation in a specific model with large extra dimensions. So the theoretical framework is that the standard model fields can propagate in n extra dimensions, and standard model fermion wave functions have strong localization at various points in the extra dimensional space, having Gaussian shape. This can be achieved by coupling fermions to scalars, which have king solution or vortex solution that localize the zero mode fermions in the extra dimension. This has the appealing feature that it can explain 4-dimensional equal hierarchies in the long distance effective theory from the locations of the fermion wave functions in the extra dimension. Furthermore, proton decay rate can be exponentially suppressed to safety by separating out quarks and leptons in the extra dimensions. I will, so the theoretical framework is that the total wave function is taken in a factorized form, where the extra dimensional part is a Gaussian shape. A is the normalization factor needed for the canonically normalized Hermitian term. And the experimental bounds sets that the length of the extra dimension L inverse be greater or equals to 100 TeV to provide adequate suppression for efficiencies to be consistent with precision electroweak constants and to be consistent with polar research. I will skip over a few parts to get to the main point, namely that consider proton decay in this scenario. So consider this operator connecting 3 quarks with 1 lepton. So we can integrate over the short distance physics associated with the extra dimension given the Gaussian wave function and obtain the suppression in the effective 4-dimensional long distance theory. The experimental bounds on these modes can be accommodated by separating out quarks and leptons like so. So for example, for n equals to 2 extra dimensions, this is of the order 8.4. So proton decay rate can be exponentially suppressed by separating out quarks and leptons in the extra dimensions. Now consider what happens for nn-bar oscillations. Nn-bar oscillations can be written down by mediating and are mediated by these 6 quark operators. So they in effect produce this nn-bar oscillation, and the effective scale is noted as mnn-bar. And given the field content, one can integrate over the extra dimensions to obtain the exponential suppression factors. And these distances are fixed from the quark mass matrix. So one can, given these values, one can note that the first 3 operators are subdominant and the 4th operator will dominate. And even the distance appearing, namely the distance of quark left to down right, is determined from the down quark mass. Therefore, we know what is delta M. And from the experimental bounds on delta M, we can infer a bound on mnn-bar. So the bottom line is that we have seen that separating out quarks and leptons in the X dimension can easily suppress proton decay, but nn-bar oscillations can occur at a level comparable to current experimental limits. And nn-bar oscillations become the main manifestation of BNV in this case. These bounds are not very sensitive to the matrix element because of the appearance of this 1/9 power. And I will also skip some parts here to discuss nucleon decay and nn-bar oscillation in left-right symmetric model with large extra dimensions. In the left-right symmetric model, B minus L is gauged as U1 B minus L. And what we see is that the effective operators mediating nn-bar oscillation, for example, these first 2 operators contains only one type of fermion, namely QR. So there are no 2 multiple fields to separate each other from. In other words, there is no exponential suppression from the extra dimensional integration. So this would actually have even larger rates than its standard model effective field theory counterpart. And as this is B minus L violating process, this basically sets a lower bound on the VR, the effective scale of the LRS symmetric breaking, which is 10 to the power 3 TeV. So although the delta V equals to -1 nucleon decay can be easily suppressed, delta V equals to 2 nn-bar oscillations may occur at a level comparable to current experimental limits. And this is even more enhanced in the left-right symmetric model. And to explain the neutrino mass matrix, one of the favorite mechanisms is the seesaw mechanism. This is the full neutrino mass matrix, where this comes from the Weinberg term. This MD is the Dirac type mass, and this MR is the Majorana neutrino mass term. Consider the simplified case of one generation. The eigenvalues split into a heavier right-handed neutrino state with mass MR and a lighter active neutrino state with a mass MD squared by MR. So choosing MD equals to 100 GeV and MR equals to 10 to the power 15 GeV, one can achieve the desired neutrino mass. But note that for our case, in the extra dimension, the natural scale for the right-handed neutrino mass is the associated compactification scale, namely 100 TeV. So this is not 10 to the power 15 GeV. But there is a scaling invariance in this relation. Namely, that you scale MR as lambda square MR and MD as lambda MD, and this relation is invariant. So in other words, we can choose the distances of the left-handed doublet leptons from the sterile neutrinos so that we produce a MEV order Dirac neutrino mass term. And we would obtain a correct neutrino masses. So this is one set of solutions for the wave function center for 2 extra dimensions. The blue are the lepton fields associated with the right-handed neutrinos, and the blacks are the quark fields. So these distances, which are denoted by a rod, a line, are actually constant from mixing matrices. So this produces the observed neutrino masses and the PMNS mixing matrix, produces the observed quark masses and the CKM matrix, results in a nearly diagonal lepton, charged lepton and down type mass matrices, thereby suppressing the flavor changing neutral current processes, are consistent with constraints on non-standard model contribution to weak decays, neutrino reactions, neutrino electromagnetic properties, non-standard neutrino interactions, and neutrinoless double beta decays. And leptons or quarks are separated from each other, so proton decay is suppressed. But N-bar oscillation only contains quark fields. That is not suppressed. I do not have much time to go into all the details of these points, but this is the overview of the solution of this case.
Can
This
you
is an
explain what are on axis here? What is eta and what is that?
Yeah.
1/2 something, 1/2 there?
That's also an eta.
It's an eta alpha.
Yeah, it's
I-
eta
1 and eta 2.
Eta 1 and
So these are the 2 extra dimensions, and these are dimensionless. So eta is defined as mu times y, where mu has this Gaussian width relation. So eta, they are basically the 2 extra dimensions, and this represents the locations of the wave center of different fermion fields in the extra dimensions.
Thank you.
So yeah, so this explicitly gives us an illustration where proton decay can be easily suppressed, whereas N-bar oscillations can be happening at rates comparable to current experimental limits. And these are consistent with all current experimental constants. So now we conclude. We have derived improved lower bounds and partial lifetimes of several nucleon decay modes. We have derived upper limits on the rates for dinucleon decays to leptons. And several nucleon and dinucleon decay modes have been considered in a large extra dimensional model. And we find that they are in accord with experimental constants. N-bar oscillations are special in the context of large extra dimensions, as it only involves quark fields. Thus, separating out quarks and leptons in the extra dimension to suppress proton decay does not suppress an N-bar oscillation, which may occur at a rate comparable to current experimental limits. We have shown that dominating operators mediating an N-bar oscillation in the left-right symmetric models in the extra dimension can be even less suppressed than their standard model effective field theory counterpart. We have presented a solution for the fermion wave function center that reproduce neutrino masses and mixing, and is consistent with current experimental constants. Thank you for your time, and I'd be happy to answer any questions.
Thank you so much. All right. Yes. Are there any questions, especially from students on this talk?
I'll go.
Okay,
Can you hear me, or should I type in the chat?
you can just get closer to the mics if you want.
Not sure. What the best
We
way
can
is.
we can hear you. We can hear you.
Okay.
Yeah, I can hear
Hi,
you.
Josh. So I'm not a theorist or phenomenologist, so I'll confess to not understanding the vast majority of this talk. But let me start out with asking the question of, so you, for all these baryon number and lepton number violating processes, you come up with different effective field theories, right?
Mhm.
Okay, so I understand the concept is you're taking all the unknown physics, whatever it is, and wrapping it up in this EFT. You're agnostic to it. The details don't matter. Is it true that all you have to do is assume that the process happens, or or are you making additional assumptions? Because what I can't understand is you're talking about all these other models where maybe there's extra dimensions, maybe there's not. So then you must have some additional assumptions beyond what's wrapped up in your EFT, right?
The only assumption for the effective field theory is that it be invariant under the standard model gauge group. So you write down operators.
Wait a second, but your effective theory violate baryon number, which standard model does not. So that it should be built in your effective theory.
Yes,
So-
standard model. In the standard model, the baryon number is an accidental symmetry. It's not gauged. So in general, for an effective operator, the baryon number can be violated. Of course,
Right,
it
but,
assumes
you should introduce the mechanism of that. That is what Charles is asking.
In a lot less detail than you are, but yes.
Yeah.
right. As we have seen, the experimental bounds on the modes are of the order of 10 to the power 33 years. So which in turn implies that the mass scale responsible for baryon number violation is actually much above the electroweak symmetry breaking scale. And hence, at the scale that we are looking, the effects of this are reasonably approximated by the effective operators, integrating out the heavier fields. This can
Well,
be
you-
coming out from,
May I continue?
Yes, you may. Yeah, I think my
Uh,
question is done.
You
Thank
said
you.
that the scale, typical scale is 100 TeV. Now there is a discussion of construction of new collider with the energy of 100 TeV. Would you consider that it will be observable effect?
right. So the baryon number violation in a collider, of course, the flux factor has to be taken into account. But yes, from a standpoint of the energy scale, of course, the effective field theory would basically break down at that scale. If you are talking about 100 TeV, where your new physics pops up, and we are achieving a scale of 100 TeV. And if there is new physics at 100 TeV, we would observe that, yes.
Okay, other questions from the room?
Would you mind elaborating a bit on what you mean by an accidental symmetry?
I just mean that it's not gauged. So baryon number is not gauged in the standard model. It just so happens that all the terms that we write down in the Lagrangian doesn't violate it.
Another way of saying that is that you have to go to non-perturbative scales. So if you have a Lagrangian and you can write down a bunch of diagrams at tree and various levels, none of those will violate baryon number. But if you go, but that assumes that perturbation theory works. When you go to a non-perturbative scale, this is no longer the case. So this is what one of the things that Tuft figured out in the 70s.
Mm-hmm. Mm-hmm. Yeah.
And actually, by the way, that's how the standard model can violate baryon number, even infinitesimally.
Sure. Yeah, the rate is very, very tiny at temperatures small compared with the electroweak scale. Yeah, but it can violate baryon number. Yeah.
Like 10 to the negative 170.
Yeah.
So
Yeah,
I should take it back that I said that there is no baryon number violation in the standard model. In a sense that you, in the mechanism which you propose, there is no. But in fact, the standard model provides the mechanism for the baryon number violation. But as you said, the tiny amount, which is practically not observable.
Yeah.
At our scale, and maybe at the scale of 100,000 TeV, it might be magnified by some mechanism.
Yeah, it might be very important for, say, baryogenesis through leptogenesis, converting lepton asymmetry into baryon asymmetry in the early universe, where the temperature is much higher, where these effects might take place.
Can I ask a question?
Yeah.
So first, thanks so much for the talk. It was super interesting. I was trying to understand a bit better this idea of protecting the proton via this large extra dimension. So at some point you said that this separation in this dimension was given by the quark mass matrix, and I didn't quite catch that argument. It was that
Right.
that itself is giving rise to this lower bound of 44 or whatever it was TeV and that parameterization you had.
Mhm. So I think this picture will explain that point a little bit better. So only the distances which are connected by a line here are constant from the mass matrices. For example, down quark mass fixes the distance of, say, Q1L to D1R. This distance is effectively fixed by the down quark mass, for example. But there are no constraints on the separation of quarks with leptons. So what we can do, we can separate out quarks with leptons by a large amount, and thereby their overlap of wave functions will be tiny. And hence, the effect of proton decay will be really, really suppressed.
And this separation is a property of the extra dimension or a free parameter or what?
It's a free parameter. It's a free
I see.
parameter.
Okay,
Yeah.
and so at some point you had a parameterization up that had, I think it was like 44 TeV at the very beginning of it.
Right, right. So that was the scale for nbar oscillations.
Yeah, so right, so I'm
let me-
thinking about nbar right now. So in the situation where you have this extra dimension that's protecting the proton, then you have the scale of this operator that's mediating an nbar oscillation. I guess I was wondering if I try to fit in this proton protection via this large extra dimension, but instead of using your effective operator for an nbar, replace that with the explicit, for example, RPV-SUSY operators. Does this lower bound apply?
So this lower bound is only for nbar oscillations, and it only applies when these are the operators. So of course,
I guess that's what I mean. If I'm talking about an nbar oscillation as given by explicit RPV-SUSY operators, are we still talking about the super high mass scale?
I understand that the SUSY is much more consistent theory than the extra dimensions. In extra dimensions, you cannot predict anything. You only say that the different branes are separated. And the separation or suppression of the proton decay is because the quarks and lepton are separated in extra dimensions. And there is no such separation for the quarks only. And this is the mechanism.
Well, I guess what I'm asking is, imagine you have the general RPV-SUSY superpotential. You allow both B and L violation in it, and normally we don't like to do that because of proton decay. But then you protect the proton via this other mechanism here. Then all we're doing is making this slide, removing the effectiveness of these operators and explicitly talking about real particles mediating these. So I'm just trying to understand that mapping for this fake thing I just made up.
Yeah, I just wanted to elaborate.
You would have to have very light mediators, wouldn't you? If you had the separation.
Yeah.
If you can actually interpret it as a physical distance, you have to have a light mediator. So I'm not sure that that's consistent with RPV-SUSY.
Just saying the combined, say, gluino and squarks that are going to be serving the same purpose as its effective operator here.
Yeah, so as long as this is a point vortex at the scale we are considering, we would still get this exponential separation and the bound would apply. But for example, if the theory is different, as I was pointing out, for example, in left-right symmetric case, the operators are different, the field representations are different. And the bound is actually on the scale of LRS symmetry breaking. As you can see, this is different. This is 10 to the power 3 TeV instead of 44 TeV. So depending on the representation of the field and the theory, the bound can be different. And of course, as you were saying, this effective vortex can be mediated by actual particles, and it would depend on their masses and combined coupling. So depending on the representation of the theory, that has to, if that results in a standard model effective field theory in the low energy effective case, then that has to obey the masses of the particles mediating has to obey that bound.
I see. Okay. Yeah, I think I understand. Thank you.
So are you saying that your predictions are model dependent? How you will treat it either in left-right symmetric or supersymmetric or SO10 or any other model? The operators will be different. And
Yeah, of
predictions
course.
will be different.
Yes, the cases for different theories would give rise to different bounds on the scale. That's right. This is because the representations are different and the I mean the field content are different. So yeah,
So
that's true.
for example, if Larry said that he would be interested in supersymmetric model, then you should concentrate on the kind of operators coming from supersymmetric model with the appropriate violation of baryon and lepton number. And then it will be at least consistent theory that you predict something which can be testable.
I think he said as long as the mass scale is high enough, then it'll apply, right?
Yeah, I
Yeah,
don't,
exactly.
I certainly am not saying that this is not consistent. This seems perfectly consistent.
What I'm saying is that at the mass scale considered, if the LRS is the actual theory, then the operator should be LRS invariant. And yes, if the SUSY is broken at a very high scale, then it doesn't matter.
I think Larry's just looking to justify more RPD searches.
I'm just gonna shove as much RPV into anything I see. Yeah.
It's like, great, a whole new range I can look at.
So I had a question on your second to
Sure.
last slide. One of your few figures. Can you explain what the meaning of these points are? You explained the line lengths, but as coming from basically mass constraints. But
Yes.
what do the locations here look like? I mean, this looks like something out of Murray Gell-Mann's dreams or something.
So they are basically the wave center location for the wave function. So
Okay.
yeah, so this is where the field is located with a Gaussian shape.
And in principle, it's allowed for these points to go anywhere on this plane. Is that correct?
Yeah, I mean, this, you can rotate keeping the arms fixed, for example, say.
Sure.
So yeah, in that respect, of course, keeping this constant rods fixed, you can change the positions of the wave function, but you have to be careful. For example, you can produce, if this, say, if these two different generations of leptons are very close together, then you would produce flavor changing neutral current effects in the effective operator, which would be much larger and not consistent with the experimental bounds. So these are chosen, although this bound, say L1, L2, L2L distance is not constant, these are chosen to be lying far apart as to obey the FCNC constant, the effective field theory limit. Yeah.
Okay.
So sorry, that following your question. Blue is lepton.
Yeah.
And black is quarks, right?
Quarks.
And
Yes.
you are saying that the distance between quarks and lepton is larger than within only lepton or only quarks.
Yes, the distance between quarks and leptons are chosen to be large to suppress proton decay. That's right.
Okay, we're over an hour, so if anyone has any last short pressing questions, we can get them in.
I had just one more, which was that, how do you
Yeah.
know what the neutrino masses are?
How do you know
how do you know what the neutrino masses are?
the right-handed
because-
neutrino masses or the
So is that all that you're limited to, is the right-handed neutrino masses
no
in
no
this particular?
So we chose a full neutrino mass matrix, right? And
Yeah.
this produces three active neutrino masses, and in
Yes.
this case, three right-handed masses. The right-handed masses were chosen to lie at the compactification scale, which is the most natural inherent scale of the theory, 100 TeV. And the active neutrino mass scale, of course, we don't know the three of the masses. We know 2 delta m squared. One of the masses was chosen to be 10 to the power minus 3 eV, just to fit to the
Okay.
model. So the delta m, it reproduces
So
the
you-
2 delta m squared.
So in principle, you have one massless neutrino.
In principle, yeah. That's right. Yeah, it only fixes, to delta m squared. That's right. Yeah.
Great, thank you. Sudha, thank you so much for giving us this talk.
Thank you.
We haven't decided that you're the first speaker of the semester. We haven't quite talked about posting videos, but would you be all right with a video of this being posted somewhere?
Yeah, sure.
Okay,
Yeah.
great. Thank you so much. All right.
Thank you very much.
Thank you everyone for joining,
Thank you.
and have a nice day.
Bye.
Yeah.
Ciao, Sudha.
Bye. Bye, Josh. Bye, Professor Kanishka.
Bye,
Bye,
Yuri.
Tova.